In cryptography, a substitution cipher is a method of encoding by which units of plaintext are replaced with ciphertext. According to a fixed system, the units may be single letters, pairs of letters, triplets of letters, mixtures of the above, and so forth. The receiver deciphers the text by performing the inverse substitution. Substitution ciphers can be compared with transposition ciphers. In a transposition cipher, the units of the plaintext are rearranged in a different and usually quite complex order, but the units themselves are left unchanged. By contrast, in a substitution cipher, the units of the plaintext are retained in the same sequence in the ciphertext, but the units themselves are altered. There are a number of different types of substitution cipher. If the cipher operates on single letters, it is termed a simple substitution cipher. A cipher that operates on larger groups of letters is termed polygraphic. A monoalphabetic cipher uses fixed substitution over the entire message, whereas a polyalphabetic cipher uses a number of substitutions at different positions in the message, where a unit from the plaintext is mapped to one of several possibilities in the ciphertext and vice versa. Simple substitution. Substitution of single letters separately. Simple substitution can be demonstrated by writing out the alphabet in some order to represent the substitution. This is termed a substitution alphabet. The cipher alphabet may be shifted or reversed or scrambled in a more complex fashion, in which case it is called a mixed alphabet or deranged alphabet. Traditionally, mixed alphabets may be created by first writing out a keyword, removing repeated letters in it, then writing all the remaining letters in the alphabet in the usual order. Using this system, the keyword zebras gives us the following alphabets. A message of flee at once. We are discovered. Ciphers to SIAAZQLKBA, VAZOARFPBLUAOAR. Traditionally, the ciphertext is written out in blocks of fixed length, omitting punctuation and spaces. This is done to help avoid transmission errors and to disguise word boundaries from the plaintext. These blocks are called groups, and sometimes a group count is given as an additional check. 5-letter groups are traditional, dating from when messages used to be transmitted by telegraph. SIAAZQLKBAVAZOARFPBLUAOAR. If the length of the message happens not to be divisible by 5, it may be padded at the end with nulls. These can be any characters that decrypt to obvious nonsense, so the receiver can easily spot them and discard them. The ciphertext alphabet is sometimes different from the plaintext alphabet. For example, in the Pigpen cipher, the ciphertext consists of a set of symbols derived from a grid. For example, such features make little difference to the security of a scheme. However, at the very least, any set of strange symbols can be transcribed back into an AZ alphabet, and dealt with as normal. In lists and catalogs for salespeople, a very simple encryption is sometimes used to replace numeric digits by letters. Example: MAT would be used to represent 120. Security for simple substitution ciphers. A disadvantage of this method of derangement is that the last letters of the alphabet tend to stay at the end. A stronger way of constructing a mixed alphabet is to perform a columnar transposition on the ordinary alphabet using the keyword, but this is not often done. Although the number of possible keys is very large, this cipher is not very strong, and is easily broken, provided the message is of reasonable length. The cryptanalyst can deduce the probable meaning of the most common symbols by analyzing the frequency distribution of the ciphertext. Frequency analysis. This allows formation of partial words, which can be tentatively filled in, progressively expanding the solution. In some cases, underlying words can also be determined from the pattern of their letters. For example, attract, osseous, and words with those two as the root are the only common English words with the pattern ABBCADB. Many people solve such ciphers for recreation, as with cryptogram puzzles in the newspaper. According to the unicity distance of English, 27.6 letters of ciphertext are required to crack a mixed alphabet simple substitution. In practice, typically about 50 letters are needed, although some messages can be broken with fewer if unusual patterns are found. In other cases, the plaintext can be contrived to have a nearly flat frequency distribution, and much longer plaintexts will then be required by the user. Homophonic substitution. An early attempt to increase the difficulty of frequency analysis attacks on substitution ciphers was to disguise plaintext letter frequencies by homophony. In these ciphers, plaintext letters map to more than one ciphertext symbol. Usually, the highest frequency plaintext symbols are given more equivalence than lower frequency letters. In this way, the frequency distribution is flattened, making analysis more difficult. Since more than 26 characters will be required in the ciphertext alphabet, various solutions are employed to invent larger alphabets. Perhaps the simplest is to use a numeric substitution alphabet. Another method consists of simple variations on the existing alphabet, uppercase, lowercase, upside down, etc. More artistically, though not necessarily more securely, some homophonic ciphers employed wholly invented alphabets of fanciful symbols. One variant is the nomenclator, named after the public official who announced the titles of visiting dignitaries. This cipher combines a small codebook with large homophonic substitution tables. Originally the code was restricted to the names of the important people, hence the name of the cipher. In later years it covered many common words and place names as well. The symbols for whole words and letters were not distinguished in the ciphertext. The Rossignols Great Cipher used by Louis XIV of France was one. After it went out of use, messages in French archives were unbroken for several hundred years. Nomenclators were the standard fare of diplomatic correspondence, espionage, and advanced political conspiracy from the early 15th century to the late 18th century. Most conspirators were and have remained less cryptographically sophisticated, although government intelligence cryptanalysts were systematically breaking nomenclators by the mid-16th century, and superior systems had been available since 1467. The usual response to cryptanalysis was simply to make the tables larger. By the late 18th century, when the system was beginning to die out, some nomenclators had 50,000 symbols. Nevertheless, not all nomenclators were broken. Today, cryptanalysis of archived ciphertexts remains a fruitful area of historical research. The Beale Ciphers are another example of a homophonic cipher. This is a story of buried treasure that was described in 1819-21 by use of a ciphertext that was keyed to the Declaration of Independence. Here each ciphertext character was represented by a number. The number was determined by taking the plaintext character and finding a word in the Declaration of Independence that started with that character, and using the numerical position of that word in the Declaration of Independence as the encrypted form of that letter. Since many words in the Declaration of Independence start with the same letter, the encryption of that character could be any of the numbers associated with the words in the Declaration of Independence that start with that letter. Deciphering the encrypted text character X is as simple as looking up the 10th word of the Declaration of Independence and using the first letter of that word as the decrypted character. Another homophonic cipher was described by Stahl and was one of the first attempts to provide for computer security of data systems in computers. Through encryption, Stahl constructed the cipher in such a way that the number of homophones for a given character was in proportion to the frequency of the character, thus making frequency analysis much more difficult. The book cipher and straddling checkerboard are types of homophonic cipher. Polyalphabetic substitution. Polyalphabetic substitution ciphers were first described in 1467 by Leon Battista Alberti in the form of disks. Johannes Trithemius, in his book Steganography, introduced the now more standard form of a tableau. A more sophisticated version using mixed alphabet was described in 1563 by Giovanni Battista della Porta in his book De Furtivis Literarum Notis. In a polyalphabetic cipher, multiple cipher alphabets are used. To facilitate encryption, all the alphabets are usually written out in a large table, traditionally called a tableau. The tableau is usually 26 times 26, so that 26 full ciphertext alphabets are available. The method of filling the tableau, and of choosing which alphabet to use next, defines the particular polyalphabetic cipher. All such ciphers are easier to break than once believed, as substitution alphabets are repeated for sufficiently large plaintexts. One of the most popular was that of Blaise de Vigenere. First published in 1585, it was considered unbreakable until 1863, and indeed was commonly called le chiffre indéchiffrable. In the Visionaire Cipher, the first row of the tableau is filled out with a copy of the plaintext alphabet, and successive rows are simply shifted one place to the left. A keyword is then used to choose which ciphertext alphabet to use. Each letter of the keyword is used in turn, and then they are repeated again from the beginning. So if the keyword is cat, the first letter of plaintext is enciphered under alphabet C, the second under A, the third under T, the fourth under C again, and so on. In practice, Vigenere keys were often phrases several words long. In 1863, Friedrich Hassiski published a method which enabled the calculation of the length of the keyword in a Vigenere ciphered message. Once this was done, ciphertext letters that had been enciphered under the same alphabet could be picked out and attacked separately as a number of semi-independent, simple substitutions, complicated by the fact that within one alphabet letters were separated and did not form complete words, but simplified by the fact that usually a tabula recta had been employed. As such, even today a Vigenere-type cipher should theoretically be difficult to break if mixed alphabets are used in the tableau, if the keyword is random, and if the total length of ciphertext is less than 27.6 times the length of the keyword. These requirements are rarely understood in practice, and so Vigenere enciphered message security is usually less than might have been. Other notable polyalphabetics include the Gronsfeld cipher. This is identical to the Vigenere except that only 10 alphabets are used, and so the keyword is numerical. The Beaufort cipher. This is practically the same as the Vigenere, except the tabula recta is replaced by a backwards one, mathematically equivalent to ciphertext equals key, plaintext. This operation is self-inverse, whereby the same table is used for both encryption and decryption. The Auto Key Cipher, which mixes plaintext with a key to avoid periodicity. The Running Key Cipher, where the key is made very long by using a passage from a book or similar text. Modern stream ciphers can also be seen, from a sufficiently abstract perspective, to be a form of polyalphabetic cipher in which all the effort has gone into making the key stream as long and unpredictable as possible. Polygraphic substitution. In a polygraphic substitution cipher, plaintext letters are substituted in larger groups, instead of substituting letters individually. The first advantage is that the frequency distribution is much flatter than that of individual letters. Second, the larger number of symbols requires correspondingly more ciphertext to productively analyze letter frequencies. To substitute pairs of letters would take a substitution alphabet 676 symbols long filled with 400 unique glyphs. However, the system was impractical and probably never actually used. The earliest practical digraphic cipher was the so-called Playfair Cipher, invented by Sir Charles Wheatstone in 1854. In this cipher, a 5x5 grid is filled with the letters of a mixed alphabet. A digraphic substitution is then simulated by taking pairs of letters as two corners of a rectangle, and using the other two corners as the ciphertext. Special rules handle double letters and pairs falling in the same row or column. Playfair was in military use from the Boer War through World War II. Several other practical polygraphics were introduced in 1901 by Felix Delerstal, including the bifid and four-square ciphers and the triplet cipher. The Hill Cipher, invented in 1929 by Lester S. Hill, is a polygraphic substitution which can combine much larger groups of letters simultaneously using linear algebra. Each letter is treated as a digit in base 26. A equals 0, B equals 1, and so on. A block of n letters is then considered as a vector of n dimensions, and multiplied by a nxn matrix, modulo 26. The components of the matrix are the key, and should be random provided that the matrix is invertible in. A mechanical version of the Hill Cipher of dimension 6 was patented in 1929. The Hill Cipher is vulnerable to a known plaintext attack because it is completely linear, so it must be combined with some non-linear step to defeat this attack. The combination of wider and wider wick, linear diffusive steps like a Hill Cipher, with non-linear substitution steps, ultimately leads to a substitution permutation network. So it is possible, from this extreme perspective, to consider modern block ciphers as a type of polygraphic substitution. Mechanical substitution ciphers. Between circa World War I and the widespread availability of computers, mechanical implementations of polyalphabetic substitution ciphers were widely used. Several inventors had similar ideas about the same time, and rotor cipher machines were patented 4 times in 1919. The most important of the resulting machines was the Enigma, especially in the versions used by the German military from approximately 1930. The Allies also developed and used rotor machines. All of these were similar in that the substituted letter was chosen electrically from amongst the huge number of possible combinations resulting from the rotation of several letter disks. Since one or more of the disks rotated mechanically with each plaintext letter enciphered, the number of alphabets used was substantially more than astronomical. Early versions of these machines were, nevertheless, breakable. William F. Friedman of the U.S. Army's CIS early found vulnerabilities in Hebon's rotor machine, and GC and CS's Dillwyn Knox solved versions of the Enigma machine well before World War II began. Traffic protected by essentially all of the German military Enigmas was broken by Allied cryptanalysts, most notably those at Bletchley Park, beginning with the German Army variant used in the early 1930s. This version was broken by inspired mathematical insight by Marian Rejewski in Poland. No messages protected by the SIGABA and Type X machines were ever, so far as is publicly known, broken. The one-time pad. One type of substitution cipher, the one-time pad, is quite special. It was invented near the end of World War I by Gilbert Vernim and Joseph Malborgner in the U.S. It was mathematically proven unbreakable by Claude Shannon, probably during World War II. His work was first published in the late 1940s. In its most common implementation, the one-time pad can be called a substitution cipher only from an unusual perspective. Typically, the plaintext letter is combined in some manner with the key material character at that position. The one-time pad is, in most cases, impractical as it requires that the key material be as long as the plaintext, actually random, used once and only once, and kept entirely secret from all except the sender and intended receiver. When these conditions are violated, even marginally, the one-time pad is no longer unbreakable. Soviet one-time pad messages sent from the U.S. for a brief time during World War II used non-random key material. U.S. cryptanalysts, beginning in the late 40s, were able to, entirely or partially, break a few thousand messages out of several 100,000. In a mechanical implementation, rather like the Rockix equipment, the one-time pad was used for messages sent on the Moscow-Washington hotline established after the Cuban Missile Crisis. Substitution in modern cryptography. Substitution ciphers, as discussed above, especially the older pencil and paper hand ciphers, are no longer in serious use. However, the cryptographic concept of substitution carries on even today. From a sufficiently abstract perspective, modern bit-oriented block ciphers can be viewed as substitution ciphers on an enormously large binary alphabet. In addition, block ciphers often include smaller substitution tables called S-boxes. See also substitution permutation network.